Today's talk, I will focus on the work we're doing in vision and audiovisual in general. And what I am going to focus on particularly is video, and I'm sure you want to hear during the conference many more talks about video. So I will give a little bit motivation and then cover a subset of the work we do in the Research AI organization, some here, some in the US, in this space. So just, let's start with where are we? I'm sure most people here know this, but there are, and it has been proven that for many tasks today, due in large part to deep learning, we have reached a point where computers can actually exceed human performance. And obviously ImageNet, at least on the top 5, speech recognition on switchboard data, are both examples of tasks that at this point computers can do better than humans. However, in video, this is certainly not the case yet. And therefore, clearly this is an area that we want to focus on for that reason. And in addition, as we'll see in a minute, obviously there are many, many use cases in the enterprise world, which is the world that we care about, who want, where video is important. And what we see in this chart, this is a data set moments in time that was created jointly by MIT and IBM in the context of our partnership with MIT. And we'll talk about that data set a little bit more soon, but in CVPR last year, there was a challenge around this, and what we saw was that the winner was less than 40% accurate, and if we look at the top 5, then it gets a little better, but overall, humans are still much better than the computer. And this data set, the goal is to classify activities. So there are 200 different activities, and the goal is really in a 3-second video to be able to classify the activity, and this is where we eventually want to be able to go. So why is video hard? What are some of the things we need to look at when we go to video? So first of all, it's temporal, right? We have a sequence of frames, it's large and so on, and there's another element in there that gives us a lot of the context of what's happening in the video, and we need to figure out how to take advantage of that information, but as a result, it becomes very big, and it's hard to analyze. Second one is we just heard, in previous talk from Professor Peleg, it's multimodal. It's not just vision, it's not just the visual signal. So we need to be able to also take into account the audio part of it and maybe some background information. And the third one is not specifically for video, but I will say that in the context at least of the audience that we care about, which is enterprises, there's also a question of really what, going from theory to practice, which is difficult in images, but in video adds even another element to it, because when you deploy something, you run into issues that you may not have thought of, especially when you're giving this technology to someone who needs to deploy it themselves in the context of their use case. And I think the example we heard before just in terms of legal and so on is one example, but there are many others, and I'll talk about them in a minute. But the good news is that there are many, many use cases, and these are all ones that we are touching in some way or other, either with some internal IBM solutions or working with some of our partners or customers, and this comes out a lot. So there is the need, people do want to deploy these types of technologies into enterprise scenarios. I do want to share still what are some of the challenges that we see our customers are facing when trying to deploy these solutions in the real world. And this will obviously impact the work that I will show, that, where we focus in terms of our work in research. So one of the biggest problems for anyone working in this space today is we don't have enough data for training. Even if we have the data, is how do we label it? And even if we already labeled it, I don't want to do it again. I want to get, something up and running in hopefully a few days, a few weeks, not in, months of work. And one more that is becoming more and more important, and I will talk about the first ones, but not so much about this one, although we do have work, is the question of explainability and fairness, and this is now becoming a very, very hot topic, and also an area we're working on, so we can talk about it offline, although I won't cover this here. I will just mention as an example This is more in the image space. We just put out a data set for diversity in faces, which created a lot of interest last week. But with the goal of really bringing out a data set that is diverse, that at least we believe has 1 million faces and is very diverse, and we believe that will let everybody build better facial recognition models that are diverse and are not biased. And this is, though, becoming a key issue before people are willing to deploy these things in some of the enterprise use cases. Okay, so what I'm going to do now is walk you through some of the specific projects. As I said, some are done here in the lab in Israel, in Haifa, and some are done in our lab in the US. In little letters down there, you can see also there are many people obviously behind this, and I will not be able to give everyone credit. So the first one is this challenge that we faced when we started working with some of our colleagues on, in this case, these are videos from media. So we do have the sight and the sound and the combination of them. And for various reasons, some of them wanting to be able to index the video better, some of them wanting to be more efficient, they said we want to be able to split the video into scenes. So clearly, the immediate thing to say is you can do shots. Lots of work have been done on shots, but what we discovered working with them is that just separating by shots is not really a good depiction of scenes, where scene is something much more semantic. And therefore, what they really wanted us to do is see if we could take the video and somehow automatically split it into scenes, where a scene is a collection of consecutive shots, but together that whole thing is the scene. Let's say this is a video of a day at the beach. There's a scene playing volleyball, there's a scene eating, but in each one of them there's going to be a collection of shots. So how can we do that and bring in the semantics? So our approach in this case was basically we started by doing some encoding of each of the individual frames and each shot basically individual frames. And then our hypothesis was that if we look at the overall distance between shots and we do some sort of an optimization, that we will, by minimizing the collective distance for each group of shots, we will be able to indeed divide it into scenes. And that is, again, more or less what we did. More information in the article, but in essence, what you'll see here graphically, what we want to do is, assuming we have like this big matrix of the distance between all the shots, we want to optimize the diagonal and get to the point that we are able to cluster it in a way that will give us the optimal selection. And it did turn out, and we'll see this in the video here, hopefully, that you can see it here, that this does yield very good results in terms of the shots. And by the way, in the paper, we did put out a data set with some of these results. It's supposed to be playing the video. We'll try again. It's working? Ah, okay, I don't see it there. Okay, so, sorry, I was looking on the screen here. But basically, okay, so you saw it running already, but just to say what you just saw, right? So the first stage is the scenes. These are the different colors. And you can see they're different sizes. They're different, I can try to play it again. They're different sizes, and they're, but they are consecutive ones, right? So, and then we extract the keyframe for each one of these. And that is needed, as I said, part of the motivation was to be able to do better navigation. And now we will see the actual scenes. And when you see some of these scenes, you will see that a scene does have, several shots. However, in the context of, the larger movie, this is a whole scene. After that, it changes to, to something completely different. So you will believe me that it works. And, in the paper, many more examples. And there is a data set that we also put up to show this. Okay, so how do we go to the next? Okay. So the next challenge I'll talk to you about is an interesting one, because this came for us again from the use case where our partner in this case said, what they want to do is really do a lot of, image, apply different types of image models, things that we know how to do, to videos. So these include, some things that we developed, like natural scene text and logo recognition, off-the-shelf YOLO, and so on. So the trivial way to do this is say, let's apply it to every frame. And the problem with doing that is, A, it could take, depending on the model, it could take a lot of time, and B, because they have to call out to the cloud, basically, to do each one of these operations, it costs a lot of money. Right, so there is like saying, hey, look, we can't really afford to go and for every frame go and call one of these models. Can you help us get to the point that we can only call a subset of these, apply the model to a subset? So again, you could do it trivially by just, say, hey, let's sample every 20th frame, 50, tell me how many you need. We'll just divide it. Obviously, that's not going to give us a very optimal result. And so what we did here is we devised a mechanism where we start by, taking the model and taking the specific types of video that we want to apply it to. We learn from this combination some characteristics of the model applied to these videos, and based on this, we're able to come up with some clues in terms of how frequent and which frames we want to, what is the characteristics of the frame that we should sample. And then, that is done offline, and now given a video, we can, start applying that. We take it in, given what we learned. This is all learned automatically in the first phase. Given what we do, we then start doing the sampling based on, what we learned. And in that sample, we only apply the model to that sample. We need to do some sort of interpolation and some sort of, apply some logic or some smarts between the frames in order to interpolate what happened in the frames that we didn't look at. And then, based on that, at the end of the day, we're able to give a label to every single frame. So let's, look at this video, and you'll see here. Okay, what you see here on the left side is applying the model to every single frame. And what you see on the right side is applying what we did, which is applying the model only to the frames that we sampled and doing some smart interpolation in between. Now, even though I told you we started by wanting to reduce the number of calls to the model, what turned out is that this actually eventually also improved the accuracy. So on the left hand, the green is good, the green is good, the red is bad. So just, flashing, you can see that there's more bad on the left than on the right. But also, if we look here on the top, as it's running, you could see a few things. In particular, you can see the difference, right? When we applied it to every single frame, it was mainly GPU calls. When we went and we ran it on all 875, and on the right, we only used 119 frames. Much less calls to GPU, more CPU, because we had to do all this interpolation. And you can also see that the accuracy grew to 0.97 from 0.93, I think it says there. So as a result, this actually ended up also improving the accuracy and also reducing the number of frames that we had to look at. So this was, obviously a very good result for us and for, our customer in this case. So now I'm going to move to this whole idea of few-shot and one-shot learning. As I said, one of our biggest issues working with customers is they don't have a lot of data, and they want machines to be a little bit more like humans and learn from fewer data points. And we have quite a bit of work on this, and at the conference there's a tutorial which will talk not just about our work, but in general, and also talk by Leonid Karlinsky, which will talk about our work. So again, just kind of high level what we're trying to do. Basically, you can see in this case, we have these two blue pictures. One is Africa dog, one is a golden retriever, and we want to really learn from one example of each. And the naive way to do it is, let's say, look at the metric space of features and just, see how it clusters. But what we can see here, the pink ones are the golden retrievers as our algorithm recognizes them. The yellow ones are the Africa set. And you can see that if we just, based on just the metric space, we would get a lot of, misclassification. So we need to do, obviously, something better than that. And again, just, this comes from many different types of use cases that we've encountered in our work. We did a lot of work on retail product recognition, logo localization. This is very important to companies. They want to be able, as you watch a video, for example, to see how many times was the logo, did the logo actually appear? Because they want to pay not a flat sum, but actually based on the number of times that someone actually saw their logo in, when we were viewing, the NASCAR race or something like that. And there are other use cases where people want to see how many times and where their logo actually appeared, and there are many other such examples that we're doing. So basically we have three recent results in this space. They've been, one was already presented at NIPS, two will be in the upcoming CVPR, and all of them are trying to approach this with different angles. This first one is really working more on the classification side. So the idea is really, can we at first learn something which will be globally. For this one, we have quite a few examples. So we are going to jointly learn embedding that takes into account both the metric space and the models for that. And for each one of these classes, basically, we learn a representation, but we learn it in a way that we will know that, in the future, when we are able to get few examples that become part of this, we will be able to distinguish them and create a new class for them with very little data. So this is what we do on the left. We pre-train, we learn these models, and then when we encounter a new class that we did not learn previously, we are able, with very few examples, at the extreme one, but hopefully 2 or 3, augment that with a few other images from our set and create a new representative that sits somewhere in the space of all the different representative classes in a way that it will be distinguishable and will be able to recognize, in this case, these two partridges. So this was approach number 1, and in our paper we showed that it improves regardless. It could improve object recognition regardless, but in particular it does provide a good solution for few shot. The other 2 works are more in the space of how can we augment. Okay, so we have some data. We don't have a lot of data, but we do have some data. But what we want to do is, from that little data that we have, create even more interesting data that can help us. So in this case, what we want to do is learn kind of multi-labels for images. And the work here has created really a novel way to perform kind of operations basically on the few images that we have to create things that we haven't seen. So basically we have a union, a subtraction, and an intersection. And again, without going into the details on how we do this, we are able to start with an image of in this case, in this example, a person, sheep, dog. We have that image, we have the label, and look at person, dog, cat, and through these operations create features, not real image, but features that can represent either the union of these. So in this case, we could have a person, sheep, dog, cat, or the intersection. So out of this, we could just isolate and get the features for the sheep, and similarly for intersection. And again, this is a paper that will appear in CVPR, and Leonid will talk about it more in details later on. And finally, again, in the same vein of how do we create interesting pictures, this one, which is called Delta Encoder, is we looked at how can we, again, take the few images we have and extract the kind of the difference between them, the delta between these images. So let's say, I have a person, that's smiling and a person that's crying and so on, but then for a different sense, I don't have these different types of features. So I can learn that this is what distinguishes between them and then apply that, in my case, to these girls to now create girls that are smiling or laughing and so on. And in this sense, really take, the little data that I had and create much more data out of it. So the last thing I will just, again, very quickly mention, I talked about the moments in time data set. And, this is three-second videos and so on. I will skip the video here. But what we've also been doing with it, and this is the work in the US, which is also, fortunately, has given us very nice results recently. This is back to the work, again, in this case of surveillance, of really wanting to be able to identify much finer grained activities in these types of things. This is a program run by the US government called DIVA, but NIST has created the evaluation for it. And in this evaluation, you need to be able to identify all kind of one person transferring a object to another person, and so on. And using various techniques, and in part learned on the moments in time data set, and then transfer learned and applied, kind of in this idea of domain adaptation, we have been able to get, the very, very good results in that case. And this is, again, one example of the work being done there, where again, we're trying, the hypothesis here is you don't really need to look at all the frames, and there's a novel way to combine all of these in order to identify what is actually happening in the video by capturing only the frames where things have changed. And again, more details in the papers. So hopefully, I've given you a taste of the types of things we're working on, some of the issues really people face when trying to apply these things in the real world, and the work that we do in IBM research to address some of these challenges. So thank you very much.